بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على خاتم الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. This is section 2.5 and it's about continuity of a function. Well, a function f is continuous at a number a if limit of f of x when x approaches a equals f of a. So the limit of the function f of x as x approaches a equals f of a. Now, this definition implies three things to happen. So f is continuous if f of a is defined. So to have f of a must be in the domain of f. So if a is not in the domain of f, then we will not be able to find f of a, and then f is not continuous at a. So that's the first condition. The second condition, the limit, this limit should exist, because if it doesn't exist, it will not be equal to f of a. So we have to find the limit of f of x when x approaches a, and it must exist. And the third condition, this limit should equal to f of a. Now notice here, this is a continuous function. As x approaches a from the right or from the left, f of x approaches f of a. So this means that the function is continuous at a. So this is the meaning of the definition. As x approaches a from the right or from the left, f of x approaches f of a. And then the function would be continuous at a. Example, this figure shows a graph of a function f at which number f is discontinuous and why. Well, f of 1 is not defined. So f is not continuous at x equals 1. Look to 3, okay? F of 3 is defined. It's somehow here, -1. F of 3 is defined, but the limit of f of x when x approaches 3 from the right is not equal to the limit of the function when x approaches 3 from the left. Okay? When we approach 3, when x approaches 3 from the right, the function approaches this number, which is, you can say 2, for example. While if x approaches 3 from the left, the function approaches this number, which is, you can say, -1. So 2 is not equal to -1. So the limit of f of x when x approaches 3 does not exist. Hence, f is not continuous at x equals 3. Look at 5. F of 5 is defined. This is f of 5. You can say 3, for example. The limit when x approaches 5 from the right and from the left of the function exists. It equals 1, for example. But the problem at 5, limit of the function when x approaches 5 is not equal to f of 5. And that's why f is not continuous at x equals 5. So these are this is a very nice example in which you find 1 here is not there in the first number at 1. F is not defined, so it's not continuous. You can find when the limit does not exist, the function is not continuous. At 3 here, the limit does not exist, so the function is not continuous at 3. And finally, this condition, which is the condition of continuity, the limit, if the limit is not equal to f of a, then the function is not continuous. And this is what's happening at x equals 5. This kind of discontinuity at 1 and at 5 is called removable discontinuity. We can remove the discontinuity at 1 by defining f of 1 equals to 1, this point. And we can, by defining f of 5 equals 1 also, the function would be continuous at 5. So 1 and 5, discontinuity at 1 and 5 called removable discontinuity. Write each of the following functions where are each of the following functions discontinuous? Well, this is a rational function. It's not continuous at 2 because f of 2 is not defined. Because 2 is not in the domain of this function. It will make the denominator 0. Here, this function is not defined at 2, but what happened? He made a definition, a new definition as a piecewise function. This function would be equal to 1 if x is 2. So now this function is defined at x equals to 2. If I ask you, what is f of 2 here? You will say 1. So this function is defined at 2 and it's defined everywhere else. If x is not 2, you use the first definition. If x is 2, you use the second definition. So the domain of this function now all real numbers. But the question, is it continuous at 2? So we have to find the limit. If we go from the right or from the left, we will always use the first definition because if x is not equal to 2, we use the first definition. If we replace x by 2, 4 minus 2 minus 2, we will have 0 over 0. Having 0 over 0, we need to factor. If we factor the numerator, it must have x minus 2 times something. X squared x times x minus 2 is minus 2 times plus 1. So this is the factored form. And now we cancel x minus 2 with x minus 2. And if you replace x by 2, 2 plus 1 is 3. So the limit of f of x when x approaches 2 is 3. And this is unfortunately is not equal to f of 2, which is 1. And that's why the function is not continuous at x equals to 2. So the limit exists and the function is defined at 2, but f of 2 is not equal to the limit. They are not equal. 3 is not equal to 1. So can we make this function continuous? Yeah, replace 1 here. Make f of 2 equals 3. Change 1 to 3. So this continuity is called the removable discontinuity because you can just remove it by changing 1 to 3. Then the limit would be equal to f of 2 and the function will be continuous. Again, another function. This function is not defined at 0, but f of x is defined at 0. If I ask you, what is f of 0? F of 0 is 1. Well, let us find the limit when x approaches 0 to check whether f of x, the limit exists or not. Well, if x is not 0, either you're coming from the right or from the left, you will use 1 over x squared. But 1 over 0 is infinity. And if you come from the right, this would be positive. From the left, this would be positive. So the limit is always infinity. So the limit of f of x is infinity, which means does not exist. It's not equal to 1. Hence, f is not continuous at x equals 0. So you can say here the function is not continuous because the limit does not exist, because the limit is infinite limit. Notice this is an example of a removable discontinuity, okay? Because f of 2 is not defined. Just define the function, make f of 2 equals to this number, it will be continuous. This is also an example of a removable discontinuity where the limit exists, but it is not equal to f of 2. So just take this closed circle up, fill this circle, and the function would be continuous. So you can make the function continuous. While this continuity, this discontinuity is not removable, it's infinite discontinuity. You cannot make anything here, okay? But it will remain discontinuous. It's not removable. It's infinite discontinuity. A function f is continuous from the right if the limit from the right equals to f of a. It's continuous from the left if the limit from the left equals f of a. It's continuous on an interval, let us say closed interval a, b, for example, if it's continuous at every number in the interval, and if it's continuous from the left of b and the right of a. So inside the interval. We don't know anything about the outside of the interval. So we need only on one side of the endpoints of the interval. If this happens, then the function will be continuous on this in this interval or on this interval. Show that this function is continuous on the interval -1 to 1. Well, limit f of x when x approaches a, where a is any number between -1 and 1, is equal to limits of 1 minus 1 minus x squared when x approaches a, and this equals 1 minus square root of 1 minus a squared, and this is f of a. So it's continuous everywhere inside this interval. We need to show that the limit when x approaches 1 from the left, okay, is equal to f of 1. So we need to show that the function is continuous from the left of 1. Well, f of x is 1 minus square root of 1 minus x squared. To find the limit, you replace x by 1. 1 minus 1, 0, so it's 1, which is f of 1. So it's continuous. F is continuous from the left of 1. Also, you can show that the function is continuous from the right of -1 when x approaches -1 from the right. So you need to prove that the function is continuous in this interval. So you come from the left of 1 and from the right of -1. And the function is 1 minus square root of 1 minus x squared. And if you replace x by 1, 1 minus 1 is 0, and the answer is 1, which is again f of -1. So f is continuous from the right of -1, which means the function is continuous on the interval -1 and 1. Properties of continuous functions. If f and g are continuous, Then f plus g is continuous, f minus g is continuous, constant times f is continuous, the product of two continuous functions is continuous, the quotient of two continuous functions is continuous, provided that g of a, of course, is not 0. Another theorem, all these functions, polynomials, rational functions, polynomial over polynomial, root functions, square root, cube root, trigonometric functions, sine, cosine, tan, inverse trigonometric, sine inverse, cosine inverse, tan inverse, exponential ex 2 to the power x, logarithmic ln x, log x to the base 5. All these functions are continuous at every number in their domains. So they are continuous on their domains. So where is this function continuous? Now, I have 3 problems. X is in the domain of len. So I have to find how to know the domain of len. So this is the graph of L and X. And the domain of len is from 0 to infinity. So X has to be greater than 0. This is one condition. Tan inverse x, I know the graph of tan inverse x. Here I have pi over 2, it's horizontal asymptote. And here I have negative pi over 2, it's horizontal asymptote. And the graph goes like this. So the domain of tan, this is y equals tan inverse x. So the domain of tan inverse is from negative infinity to infinity. So I have no problem with x here. Now x squared minus 1 is in the denominator, so it cannot be 0, which means x cannot be positive or negative 1. So the function is continuous everywhere except at 1, negative 1, and x has to be greater than 0. So we have to start from 0. So from 0 to 1, union from 1 to infinity. The function would be continuous on this interval because we are checking, we have a condition that x has to be greater than 0, but 1 shouldn't be included. Negative 1 shouldn't be included, but negative 1 is already not in this interval. So from 0 to 1, union 1 to infinity, this is actually the domain of this function, and it's where the function is continuous. So you can say the same question now. When I ask you where is the function continuous, you just find the domain of the function. If f is continuous at b and limit g of x is b when x approaches a, then limit f of g of x is f of b. So this is the composite function. The limit now can goes inside the composite function. Okay. So to evaluate this limit, now this function is inside sine inverse. So you can just write sine inverse and take the limit inside sine inverse when x approaches 1. Now, sine inverse should be continuous here. So when we evaluate this limit, we will find out what is the limit, okay? How to find this limit? If you replace x by 1, 1 minus 1 over 1 minus 1 is 0 over 0. So we need to do something. If you remember, since we have a square root, we can multiply by the conjugate, 1 plus square root of x. Or in fact, you can use difference of two squares to factor 1 minus x to 1 minus square root of x times 1 plus square root of x. Okay, if you multiply by the conjugate, you will get the same answer. These two will be cancelled, and we will have sine inverse of now 1 over, if you replace x by 1, 1 plus 1 is 2. Sine inverse is defined at half, and you can be in radian mode always, and ask the calculator to find sine inverse of half. It is easy to find. It's 30 or pi over 6. So that's the limit. When x approaches 1, the limit of sine inverse this function would be pi over 6. If g is continuous at a, f is continuous at g of a, then the composition of the two functions is also continuous. So g has to be continuous at a, and f is continuous at g of a. Where are the following functions continuous? Now x squared continuous where? This function x squared, y equals x squared. It's continuous everywhere because the domain all real numbers. What about sine of this function? So x squared will give you always the range of sine. Well, the range of x squared would be from 0 to infinity. So sine any number from 0 to infinity is okay, is defined because the domain of sine even from negative infinity to infinity. So there is no problem. Sine has the domain from negative infinity to infinity, x squared domain from negative infinity to infinity. So this function is continuous everywhere. So h is continuous on R from negative infinity to infinity because the domain is from negative infinity to infinity. This is the end of this section. I hope you enjoyed continuity. Thank you.